Hello, my name is Reda, and on behalf of my co-authors, I'm very happy to be presenting our work on how to improve inference and reduce the risk of false discovery from visualizations. Now, visualization is great because it allows us a way to look and peek into datasets and try to find patterns that might be interesting. Some of the data that we might be collecting could at first be, or seem at least, statistically identical, but when we plot it, we actually discover very different patterns that underlie these datasets. Some of these patterns can be quite revealing and insightful and useful to investigate further, but other patterns that we see in visualizations could be purely incidental. So, for instance, there happens to be a correlation between chocolate consumption and the number of Nobel laureates in a country. Now, this observation has generated a paper which put forth the idea that the flavonoids contained in chocolate can improve cognition and can in turn help generate outstanding ideas. But as it turns out, it's not just chocolate, but also the number of IKEA stores seems to be correlated with Nobel Prizes. So there are many underlying causes for these spurious and other misleading patterns that we might come across. And one reason is that with almost every dataset we look at, that dataset represents typically an incomplete sample. And therefore there is uncertainty in the measurements as well as natural variation that is difficult to eliminate. And it's not too difficult to imagine how an interesting visualization could be entirely reversed given a different sample from the same source. When we consider the fact that people usually look at multiple visualizations when they're analyzing data, there's almost a guarantee that with sufficient exposures, there will be something interesting in the end, although that interesting pattern could be simply noise. Now, the problem of multiple comparisons is typically controlled in formal statistical modeling, but it's often unaddressed in interactive visual analysis tools. In fact, visualization tools are designed around this very idea that people should be able to view a large number of projections and slice and dice their data on demand as they wish. Now, this can inflate the risk of false discovery, and in fact, by one study, up to 60% of visualization insights may be false. Our goal in this work is to evaluate potential design interventions to visualization systems that could help reduce the risk of overinterpreting spurious data. And the intervention that we're exploring in particular is to invite analysts to share their mental models and hypotheses with the system prior to data exposure. After we elicit their informal model, we can display the data sample that we have at hand. And considering then both sources of information, the analysts can make up their mind on what conclusions to take or what inferences to make from this dataset. Now, an advantage of this workflow is that it is more in line with how experienced scientists and researchers work by first positing a hypothesis and then testing the data against this to refine their model. But the intervention could also have a prophylactic effect. If the analysts encounter data that is too extreme or too improbable, they could consciously modulate how much they're learning from that data and potentially use their prior model as the basis for their inference. Belief-driven interactions for visualizations have attracted research from the SIGCHI and visualization communities, with studies and prototypes on how to visually elicit user beliefs and models and how to present data in relationship to those models. In an earlier work, we introduced a prototype tool that mixes these belief-driven interactions with traditional visualization functionalities. In this prototype that you see here, users can create data views, specify their expectations in various kinds of charts, and still use exploratory functionalities like brushing and linking, which people have come to expect from these kinds of systems. But the question is still whether these interactions can improve the reliability of conclusions, particularly in the presence of noisy data. So our first research question is, what are the effects of prior elicitation on the accuracy of inferences that people make through visualizations? We answered this question in a crowdsourced experiment. Workers were exposed to a series of scenarios and were asked to make inferences from potentially noisy datasets. In every stimulus, we presented participants with a context, such as US tech workers, and we asked them to respond to a prompt like, what is the relationship between a programmer's income and the amount of leisure time that they have? Participants first provided us with their prior model of this relationship, which they furnished through an elicitation device seen here. Now, this device allows them to set two things. First, the direction of the expected relationship, and secondly, the strength of the relationship they expect to see. Now, prior to the study itself, we formulated a ground truth model for this prompt based on the crowd wisdom from a different set of workers. We sampled this model, and we show the resulting visualization to the participants, and we asked them to tell us what they think the relationship is using an open-ended response. And because we know the real answer, we can code those inferences for their consistency with the ground truth. Now, occasionally, instead of showing them a visualization that is consistent with the model, we present them with spurious samples to see how they react to it. And the main result that we're interested in is whether belief elicitation prior to data exposure, which is the intervention that we're testing, will affect the accuracy of the inference. And we compare this to a control condition where we still elicit participants' model, but only after data exposure. So the main difference between the two conditions is only in the timing of the intervention, which is to say whether it comes before or after data exposure. Now, the study included stimuli where the ground truth sometimes indicated a correlation, either positive or negative, and sometimes null models with no correlations. We also included two sample types, large and small, and of those small samples, a certain percentage, about 35%, were spurious, meaning they were inconsistent with the underlying ground truth. Now, we determined this percentage through simulation by sampling randomly and seeing what portion of those simulations yielded a visualization that's misleading. Now, onto the results. Here in red is the main intervention, which again is elicitation before data exposure, versus control, where elicitation happens only after exposure. We find that participants in the intervention made more accurate inferences on average, and specifically they were about 20% more likely to discover the true model compared to the control group. Now, also looking at specifically at the rate of false discovery, which is to say the percentage of null models that were incorrectly set to indicate a correlation by participants, here we also see a lower percentage for the intervention, about 10% lower, which does suggest that it has some protective effect against extreme or improbable samples, as we hypothesized. Now, breaking down the results by sample type, we do see that inference accuracy is affected by whether the sample is small or large or small and spurious. And consistently throughout all of these sample configurations, we do see a better inference rate for the intervention group, and here in red. And looking at the results by the type of ground truth, again, which is to say whether there is a correlation or not in reality, we also see better inference for the intervention across the two model types. But interestingly, there's also a large main effect here, and participants were generally much more likely to be tricked by spurious samples when the ground truth indicated a no correlation. So even with the improved inference, we still see a large number of participants who were tricked, reporting things like people who consume caffeine tend to be shorter on average, which of course is untrue. And this overall has contributed to a relatively higher rate of false discovery in the study. Although the interventions still seem to have some tempering effect and lowering this tendency somewhat compared to the control. So coming back to our research question, can eliciting and incorporating people's prior improve inference from noisy visualizations? Our study suggests that the answer is yes, and there seems to be a reliable effect here. And specifically, people who underwent intervention generally made more accurate discoveries from across all sample types. We also found evidence that those who furnished their priors were a little bit more skeptical of the data, particularly when it contained spurious patterns. This lends support to the idea that there is a protective effect against extreme data that's generated by incorporating priors, and perhaps much like how priors can function in a Bayesian workflow when there is limited data available. Now, the effect is somewhat moderate, though, translating to about 20% better inference and 10% fewer false discoveries. And although those are potentially concrete gains for this minimally intrusive interaction, it's still important to put this effect in context and note other biases that analysts may be subject to, like incentives to find any positive outcomes at all costs. The implication for this work is that model elicitation could, and perhaps even should, become a standard feature in visualization tools. There's some evidence to suggest that analysts will embrace this feature if it's there and will use it frequently, which could in turn contribute to more generalizable conclusions from visualizations, as this study suggests. One thing to note, though, is that the intervention will mostly work when priors do provide a useful signal to weigh against data. So there's always a risk that analysts could be misinformed or could attach even more weight than called for to their priors, which could in turn lead to confirmation bias. Now, in the paper, we explore a couple more additional interventions to try to alleviate this risk, including highlighting counter evidence or data that deviate significantly from the prior to try to call attention to those. The details are in the paper if you're interested. And with that, I would like to thank you all for your attention, and I would be happy to take any questions.